So 3.2, we're talking about the derivative. So what we said last time, and I'll make it more formal now. If the limit of f of x plus h minus f of x over h as h goes to 0 exists and is finite, we say f is differentiable at x, and call the limit, let's say denote the limit by f prime x. So if this limit exists, we call it f prime x, and we say the function is differentiable at x. Yeah, Mariah.
Does that mean like every point in its domain?
Just at x itself. Okay. So if this limit exists for some x,
Oh, I see. Yeah.
for some x, so you have some function, you choose a point x. Yes, last time we were calling the point a, but today we're going to call it x. Okay. It doesn't matter. Say. So if at that point the slopes of the secant lines tend to a limit as you let the second point tend towards the first, then we say the function is differentiable there. Okay. And denote the limit by that. We call the function f prime x, f prime the derivative of f, the derivative. So this function, if we think about this f prime is a function of x, right? At each point x, you get a different slope. You get a different slope of the tangent line, and so it itself is a function, and we call that thing the derivative. Okay. So for example, last time we saw if f of x was x to the sixth, then f prime x turned out to be 6x to the fifth, 6x to the 5. Right? We also saw that if f of x, if f of x was the sine function, then f prime x turned out to be the cosine function. Right? The derivative of the sine turned out to be the cosine. For this first example, we actually saw, or at least we made it plausible that whenever you have some x to the n, and n is some natural number, then f prime x was nx to the n minus 1. Right? This is what we call the power rule. Okay, so we're just saying the same thing that we said last time, just putting some more formal language on it. Okay. If that slope tends towards a limit, if the slopes of the secant lines tend towards a limit, we say the function is differentiable at x. Okay, and so geometrically, this is all from last time. This f prime x is the slope of the tangent line. So the tangent line to the graph of f at x, f of x. Okay, and in some sense, the way you want to think about being differentiable is this. Being differentiable at x is basically the same thing as saying that f's graph can be somehow well approximated by a line at this is important. When the scientists talk with me, they say, make sure that you get this across to students, that being differentiable means that you are well approximated by a line. Your function basically is linear there, or it's very close to linear there. Okay, so what we mean by this is that, here's sort of the rough notion of it. Okay, that if you look at something, you look at your function, and well, from a distance, it doesn't look like a line, right? From a distance, it doesn't look like a line. But if we pick a point here, on the graph, and we zoom in on that point, you keep on zooming in on that point. As you get closer and closer to it, well, it looks more and more line-like, right? It looks more and more like a line. If I'm right here, it almost looks exactly like a line, right? Okay. So you say, okay, that function, that basically means that it's differentiable. Okay. Whereas for a function that has something like this, right? A function that has a point like this, if I look at that point, I say, okay, well, from a distance it doesn't look like a line, and so I'm going to zoom in on it. I'm zooming in on it. It still doesn't look like a line, right? No matter how far in I go, right? It still has this angle to it, right? It doesn't look like a line. Okay, and so this we saw last time. This is an example of something that's not differentiable at a point. Okay, so what this basically means is, as you zoom in, it gets more and more line-like. Okay, that's roughly what differentiability means. Okay, okay, so your function is basically line-like. Okay. So I can give you the sort of fancy explanation. Okay, so I'm going to give you the fancy explanation of this. Okay, don't worry too much if you don't get it, but I'm hoping that you'll get it. Okay. So why does differentiable f(x) mean line-like? Line-like. Why does this happen? Okay. I'm going to use the point C. Okay. Differentiable at some point C. Why does it mean that you're line-like there? Okay. So line-like at C. Line-like near C. That should be out. Okay. So f prime C, right? F prime C, that's a limit of f of x minus f of c over x minus c is reciprocal to c. Right? That's just the definition of differentiability. Okay. Right. No one objects to that. That's the same thing as saying that the limit of f of x minus f of c minus f prime c x minus c over x minus c equals 0. Okay. All I did was move this thing to the other side, and then I moved it into the fraction. Right? I've moved this f prime c over to the other side. It becomes negative f prime c, and then I moved it into the fraction by multiplying it by x minus c. Okay. Everything okay? So let's say it this way. Let me call this thing. Let me call this upper thing R of x. Okay. So f of x minus f of c minus f prime c x minus c is r of x times x minus c. Right? If I call the numerator r of x, that's what I'm saying here. Let r of x be the numerator. Right? I'm just okay. Let r of x be the numerator, then this is true.
Wait, then y times x minus c? The whole numerator is r? Oh, I see. Yeah, never mind.
The numerator
Yeah.
is r of x, right? So this. I'm sorry. No, you're right. You're right.
Okay.
This is r of x. No, this is r of x.
Okay.
This is r of x, right? Sorry. Actually, I'm sorry. Let me let the whole thing be r of x. That's what's looking. The whole thing is going to be r of x. Then this is true. Okay.
Then how did you get the denominator over the other side?
I just r of x. I'm going to call this whole thing r of x, right? So let me call this thing r of x, right?
Yeah.
Then multiply both sides by this, right? Let me call this thing r of x. And so what I'm saying is that this equals this, and the limit of r of x is 0 as x goes to 0. X goes to c, excuse me. Yeah, Claire.
How do you know that?
Because r of x is this. I'm just calling this thing r of x.
Right.
Right, and we know the limit of r of x is 0.
Why? How do we know that?
This is r of x. The limit as x goes to c of r of x is 0. I'm just writing the same thing again.
Oh, okay.
Okay, so we know this. Let me call this thing r of x, and I'm just going to say the limit of r of x is 0, right? Because that's what this is saying. This is saying the limit of r of x is 0.
Right, so when you took the f prime of c to the other side, you made that makes
Yeah.
that side 0.
Yeah.
Okay.
Yeah. Okay. Is everyone all right? Anyone confused? Leah, are you confused? No. You sure? It's okay. So what do we do? We're saying, what does it mean to be differentiable? It just means that this limit equals some number. What does that mean? Well, that means that if I pull this thing over, then this thing is equal to 0, right? So that's the second statement, right? The limit of this thing is 0, right? And if I call this thing r of x, what I'm saying is that the limit of r of x is 0, where r of x is this thing here. Okay. So now I'm going to rewrite. So all I'm doing is just rewriting over and over. Right? It's like saying, I am Sam, Sam I am. Right? Right? You're not really saying that much different. Okay, so now I'm going to rewrite it again. I'm going to say that f of x equals f of c plus f prime c x minus c plus r of x minus c, and the limit of r of x is 0 as x goes to c. Right, so all I did was move these guys to the other side.
And is that supposed to be one like continuous expression down there?
Yes.
Okay. Gotcha.
Okay, so let me write it up here so you can see it. Right. So f being differentiable at c means f of x equals f of c plus f times c x minus c. F times c x minus c plus r of x minus c, where the limit of r of x as x goes to c is 0. So now I've rewritten this. I've rewritten differentiability, 4 times or so, and you see what differentiability means. It means that, well, as x gets close to c, this term here vanishes. This term here gets very small. Right? This term goes to 0. In fact, it goes to 0 very fast because r of x goes to 0, and x minus c goes to 0. So it really goes to 0. It's a product of 2 things that go to 0. Okay. So basically, near c, f of x is f of c plus f prime c x minus c. What is this thing here? Does anyone recognize this? Can anyone figure out what this is? It's a line. This is a line, right? This is a line that, this thing here is a line, which has slope what? What's the slope? F prime c. And passes through. Well, what's its value at c? F of c. C, f of c. Right? A line which has slope f prime c and passes through c, f of c. Right? In other words, what is that thing? Here's c, here's f of c, here's the slope, right? That's the tangent line. That is the tangent line. Yeah, Mariah.
Wait, why can you say that on the right side of the equation, x minus c goes to 0 and it's a product of zeros, but then the other x minus c, you don't say that? That it becomes 0?
Yeah, I mean, you could say that it becomes 0, but then you're sort of ignoring. What we want to see is what we want to focus on is that the thing is line-like.
Won't they go to 0 at the same rate? You mean the right side of the stuff?
Not exactly, because this will go to 0 faster.
Oh yeah, I see.
Right?
Okay.
This because you've got something going to 0 times something going to 0.
Okay.
Right. So it's true. You could say, well, as x goes to c, this also goes to 0. But then the information you get out of it is that your function goes to f of c there, which is useful. But that's not what I want to focus on right now.
Mm-hmm.
Right. So but we'll actually focus on that in a second. So yeah. So not bad. Okay. So but the point is this: that being differentiable. What does being differentiable mean? It means that f of x is basically the tangent line. As you get closer, as x gets close to c, your function is the tangent line plus something that vanishes. Your function is the tangent line plus something that vanishes in a very fast way. Okay. So being differentiable at c means f is basically f is f near c is the tangent line. F of c plus f prime c x minus c plus something that vanishes quickly. Okay. So this is what it means when we say being differentiable means you're line-like. Being differentiable means you're line-like. Okay. Any questions? Maybe some of you have given up. I'm going to close my brain. My brain is closed. Those of you who still have a crack open, any questions? Any questions?
So we have to regurgitate this all the time?
No. Rather, I'd like you to, but can you understand it is my real thing.
That part I got.
Right? This is the definition. This part I just did arithmetic. I moved this to the other side. This part is just the same thing as this. We call this thing R of x, right? This is the same thing as above, right? And then you do more arithmetic, and you say f of x is the tangent line plus something that vanishes. And that's it. Okay. Anyway, so being differentiable basically means that you are line-like. Being differentiable means that you are line-like as you zoom in close to C, right? And that's why, like, when I go like this, this is exactly this part here. Okay. Okay. So enough of that. So we did these sorts of calculations before. I don't think I'll do another one. Let me say that there's a bunch of different notations for the same thing. Some people write f prime c. You could also write this as df dx at c. People write this also as ddx of f at c. People write this as df dx at x equals c. Some people write this as a big D of f at c. Okay. All these things mean the same thing. These are all different notations. Yeah.
Can you also use dy
What?
dy over dx?
dy dx. Well, there's no y here, right? It's just f. Yeah. So I'm not gonna. If you say that y is f of x, then you could say dy dx. Yeah. You could also write this as dy dx. Yeah. Okay. Okay. So next we're going to talk about something that happens with differentiable functions. So differentiability and continuity. Or actually, maybe. Okay, let me actually do something else first. Okay. Properties of differentiability. Properties of differentiability. If f and g are both differentiable at c, then the sum is differentiable at c. Right? So that's part one. Part two, if f is differentiable at c, and alpha is some number, then alpha f is differentiable at c. Okay, so the use is like this, right? If you know that your functions are differentiable, then the sum is differentiable. So for example, last time we said x to the 6 is differentiable. We said the sine function is differentiable, right? So now by this thing, we know that if we differentiate this, oh, I'm sorry, with the derivative of the sum is going to be what? What do you think it's going to be?
5 or 6x.
I'm sorry. Well, in general, if you have two functions, f and g, and they're both differentiable, what's going to be the derivative of the sum? What do you think? What do you think it will be? The derivative of the sum will be the sum of the derivatives. Right, will be the sum of the derivatives. And here, the derivative of some number times a function will be what? What do you think? The number times the derivative of the function. Okay. So for example, going back to this thing, right, we're now taking the derivative of the sum. So it's going to be the sum of the derivatives, right? What's the derivative of the first guy? 6x to the 5. 6x to the 5, right? And then the derivative of the second guy is going to be cosine x. So the derivative of the sum is the sum of the derivatives. You don't have to, work it out again. You don't have to work it out again because it'll just turn out to be the sum of the two pieces. Yeah. Okay.
Is the derivative of cosine of x sine of x?
No, it isn't.
Okay.
But it turns out to be negative. It's a negative sine x.
Okay.
Application number 2. If I have something like this, x to the 6, x to the 6 plus, say, 5x cubed. Well, what's that going to be? Actually, don't put it out, but write down. Take 10 seconds and write down something. Okay, turn to somebody next to you and say, I wrote down this. Okay, so what's the answer?
So
6x to the 5th plus what? 15x squared, right? Because you've got this 5 here, right? So you're going to have 5 times the derivative of x cubed, right? 5 times the derivative of x cubed, right, is going to be 6x to the 5th plus 15 squared. Okay, yeah, Asha.
Is there a preferred notation?
Is there a preferred
Like
notation?
the
No.
Why are there so many different ones?
Why are there so many different ones? It's because of a dispute, actually, at the beginning of calculus. So this is what's called the Leibniz notation, and this is what's called the Newton notation. Okay, Leibniz and Newton basically did a lot of calculus, or were sort of the great initial promoters of creators and promoters of calculus. And and each of them sort of claimed priority over the other, saying, I created calculus first, you were just an imitator, you plagiarized me. And Leibniz also says the same thing back to Newton. Okay. So there's sort of a fight at the beginning. And it's and sometimes it's more convenient to use Leibniz notation, because if I wanted to write this, I'd have to write it like this. Let f of x be x. Then f prime x equals 6x to the 5 plus cosine x. Right? If I wanted to write that the derivative of this is that, I write it in this way. In the Newtonian notation, I write it this way, but it's a bit quicker to write it in the Leibniz notation. But people use two.
Do you have a preferred form?
Do I have a preferred form? I generally stick to the Newton notation, but as you see, when it's convenient, I'll gladly throw it in. Yeah, but it should be said that in fact, the person who discovered the notion of derivative before Newton or Leibniz was, I think, Fermat. Fermat, the lawyer, who I believe we mentioned before. Have any of you heard this name, Fermat? Fermat? F-E-R-M. So he's a lawyer. There's actually like this huge story about Fermat because he was a lawyer but really a great mathematician, and he would solve problems, think of and solve these really impossible problems, and then he would announce them to the mathematical community, saying, "I can show such and such marvelous result. Can you?" And then, so he had this whole list of things that that he showed, but did not reveal the answer how he did it, and then died. Okay, so there's this whole whole collection of things that Fermat claims he had proven. Over the decades, was went after and got them, but then there was one left, and it's called Fermat's last theorem. Okay, and that one was not solved until until 1994. Right, so this is more than 350 years later. It took 350 years for people to figure out how to solve Fermat's last theorem. Right? And this thing, basically nobody thought it was possible to solve Fermat's, to show if it was true or not true. And in fact, people didn't even dare to approach it because so many people had failed at it. It was seen as like a sort of quixotic waste of time. But then, in 1993, Andrew Wiles of Princeton, who was actually my first teacher at Princeton. 1993, this is after I graduated, but 1993, Wiles announced, "I just got the proof of Fermat's last theorem." And like the whole world goes into uproar. Well, not the whole world, but the whole mathematical world goes into uproar. And there's this picture on the front page in the New York Times. There's this picture of Wiles like got this huge smile on his face. And Wiles is from England. He's a very reserved man. So let us define the field. He didn't smile like that when we saw him. But anyway, so he had this huge, this really wonderful smile on his face. Anyway, so Wiles announces that he's got the proof. But then, like a few months later, he says there's trouble. There's an announcement. There's trouble with the proof. And the thing is that if there's a trouble with the proof, it's basically the end. Like if there's any, there's a Nova documentary about it. And they say building a proof is like building a stack of cards, right? Building a house of cards. If one card falls, the whole thing falls, right? So he says, okay, there's problem with the proof. Right? Like everybody's nervous, right? But then, well, maybe I should. Well, I should probably let you watch the documentary. But then he has this sudden revelation, and he publishes with a student of his, a former student of his. He publishes something that fills in the proof and completes Fermat's last theorem. So.
What is the theorem?
Oh, it's actually something that is really easily stated. So you know the Pythagorean theorem, right? A squared plus b squared plus c squared, right? Do you know any whole numbers that satisfy the Pythagorean theorem? Probably you do. 3, 4, 5, right? 3 squared plus 4 squared plus 5 squared. 5 squared plus 12 squared equals 13 squared. You can, in fact, there are infinitely many triples that satisfy this relation. So what Fermat said was that if you change the 2 to any number bigger than 2, then it's impossible to find numbers that satisfy this. So for 3, there are no numbers that work. For 4, there are no numbers that work. For 5, there are no numbers that work, etc., etc. Okay. So so one reason people sort of didn't want to put that much effort into Fermat's, sort of gave up on Fermat's last theorem was because it was sort of like, well, if you get it, what's the point afterwards? But what happened was that in the late 20th century, this Fermat's theorem got tied to some really important mathematics, and it was shown that if this major thing in mathematics was true, then Fermat would have to be true. And so what Wiles did was go after that thing that implied Fermat's last theorem. Yeah. So and got it. Anyway, so at the time, an article came out in the Chicago Tribune saying that that graduate students, math graduate students at the University of Chicago had gone out on the streets, burning things and turning cars over, and, like stopping random passersby, asking them mathematical problems, like harassing all sorts of people. It was a joke column, of course, but it's nice to think that that's what we did. Anyway, yeah. Okay, what were we talking about? What were we talking about? I wasted too much time. Shoot. Okay. So, yeah, right. So I think so. I'm going to skip something. So anyway, so here are two things that allow us to get more and more out of the things that we have, right? Any sort of combination that comes from sums and multiples of numbers, you can differentiate, right? So, right, if somebody gives you a long polynomial now, right? Somebody gives you a long polynomial, I could have made this polynomial much longer. Now you can differentiate it using the power rule plus these two facts, right? The sum, you just break. You say, well, the sum of these guys is just the derivative of the sum is the sum of the derivatives. The derivative of any multiple is just the multiple of the derivative, etc. Okay, so let me go back to what I was going to talk about earlier, which is continuity and differentiability. Continuity and differentiability. So let me ask you, if a function is differentiable, what do you think? Is it continuous?
Yeah.
Yes.
Why?
If there's a jump, there won't be a limit at that point.
If there's a jump, there won't be a limit of the function at that point. But what about the slopes? What about the slopes of the secant lines? So, but you're right. If the function is not continuous there, it's not going to be differentiable there, right? So, in fact, differentiability, let's see, implies continuous. Okay, or to say it the other way, not continuous at C implies not differentiable. Right. So here's the formal way of saying it. You say, well, look, f is differentiable at C. That means that this limit exists. Right. Remember what continuity meant. What did continuity mean? What did continuity mean? Continuity meant?
The limit as x goes to c and f of x equals f of c.
Right. Is it true? Does that follow from this? Well, you say, well, look, right. This equals some number. Right. Okay. So, does anyone see why it should happen that f of x actually turns into f of c from differentiability? Can anyone see it? Why the limit of f of x as x approaches c becomes f of c? Let me show you. If I multiply, say, both sides by the limit of x minus c. So I'm going to multiply both sides by the same thing. Multiply both sides by the same thing, and here we get the product of limits. Well, what's the product of limits? It's going to be the limit of the product, right? So here we're going to get the limit of f of x goes to c, as x goes to c. And on the right-hand side, what do I get? As x goes to c, what's the right-hand side? Zero. Zero. Very good. The limit of f of x minus f of c is 0. In other words, your function is continuous.
I'm sorry, could you explain that?
So this is what differentiability means. I'm going to multiply both sides by the same thing.
Wait, why would you like think to do that?
I think to do that because look at what I'm trying to get information about. I'm trying to see that this limit is 0, right? So I'm going to try and isolate that by multiplying by this thing so that I can cancel out the x minus c.
And then what?
So I multiply both sides by limit of x minus c. Is that okay?
That's absolutely.
Okay. Then I say, well, the product of limits is the limit of the product, right? So I'm going to multiply this, the product, right? So I get this times this. The x minus c's cancel, and on the left-hand side, I'm left with this,
Okay.
right? On the right-hand side, what's the limit? Well, it's 0, because as x goes to c, this goes to 0, and this is just some constant. You have a constant times x minus c as x goes to c. So you have 0 times a constant.
Oh, okay.
Okay, so the right-hand side turns into 0, and lo and behold, you see that continuity pops out of differentiability. So being differentiable means that f is continuous. Okay, differentiability forces continuity, but not the opposite, right? You can have a continuous function that is not differentiable. Yeah, Claire.
How is the limit of x goes to c of x minus c times f prime of c 0?
F prime to c is just some number, right?
Okay.
Like 5 or something, right?
Oh, and that's 0.
And this is 0, so you get
Okay.
5 times 0. Let me do quickly just one example. There are more examples in the notes, but let me do quickly one example of a tricky differentiability problem. So if I ask you for the derivative of this, well, you're going to have to take the limit of the square root of x plus h minus the square root of x over h as h goes to 0. Right? Okay. Which is a little bit tricky. Does anybody have an idea of how to do it?
Use the power rule.
No, so the power rule, as you relied on Pascal's triangle. There was no row of Pascal's triangle corresponding to a half. So we can't use the power rule, even though it actually turns out to be true for all numbers. Okay, but we can't use it. Okay, we're gonna have to do it with our bare hands. So what we're gonna do is play a trick. It's an algebraic trick. We're going to multiply by 1, and this is our 1. Why do we do that? Because then we have a difference of squares on the top, right? A minus b, a plus b, right? So we get a squared minus b squared over h. Keep on.
Sorry, why can't we use the power rule?
We can't use the power rule because the power rule relied on Pascal's triangle. And there's no row of Pascal's triangle that corresponds to a half. Right? Pascal's triangle gives you the coefficients for a plus b to the n, where n is some natural number, right? But not for n being a half. Okay. Like I said, it turns out that the power rule actually is true for all numbers, but we can't use it at this point. Everyone all right? I'm sorry to keep you over. Let me just rush through it. So what you get, the x's cancel off, right? You get h h on the top, h is a factor on the bottom, and you end up with the limit of 1 over root x plus h plus root x as h goes to 0. And so you get 1 over 2 root x, which is what you would get if the power rule were true for x to the 1/2.
Wait,
So
can you
just-
do that last step again?
Sure. Right, you've got 1 over this plus this. As h goes to 0, this becomes root x.
Oh, yeah.
Right? So you get root x plus root x, 2 root x.
But does it show that the power rule is true?
This doesn't show that the power rule is true for all numbers. It shows it's true for x for n equals 1/2. Later we'll see that it's actually true for all numbers, but not yet.